Hi everyone. I'm recording this lecture, which is about results reporting and hypothesis testing. What I'm going to cover today is, first, I'll start with what we've covered last week, and then I will discuss what we are supposed to cover this week, which is included in this lecture and also in the next lecture. So first, let me have a quick look at the what we have covered last week. So last week we talked basically about regression analysis. We talked about how we have two variables, and one of which is the dependent variable. We called it y, and this dependent variable is determined by changes in the independent variable x. And we learned that regression does not establish causation, and if you need to learn or to decide which variable is the independent and which variable is the dependent, you will need to rely on theoretical consideration. Also, if causality exists between the two variables, as long as we have a single equation model where we have only one equation, that means causality will flow only in one direction, and we explained that this will happen from x to y, from the independent variable to the dependent variable. Also, we learn about linear regression model means linearity in the parameters, not in the variables. So the variables could be linear or non-linear. But to have a linear regression model, we need the parameters beta1 and beta2 to be linear. We've covered the simple regression, the most basic model, which we have two variables, x and y. So x is the independent variable, y is the dependent variable. Also, we learned that in regression analysis, we usually rely on a subgroup of the population because we cannot obtain data about the entire population, and for that reason we try to obtain or to collect data from the population or about subgroup of the population, which we call a sample. So using a sample, and if that sample is representative, if it is a good representative of the population, then whatever conclusion we're going to make based on the sample, we can make some inference, or we can make some conclusion about the population from which this sample is true. So that's what we covered. Also, we talked about some desirable properties of the estimators. We talked on unbiasedness, and we said that we're looking forward to have an estimator that is unbiased, which means, if you remember, we said the values of beta1 and beta2 will change when you change the sample. So if you pick up another sample, you will have different values of for beta1 and beta2. So every time you will do that, the value will change. But on average, or the expected value of this estimator, which beta hat in our example, should equal beta, which is the true parameter. So the mean of the sampling distribution for our estimator is equal to the true population value, which is beta. That is unbiasedness. The other property we talked about, we covered last week, was efficiency. And if you have among a number of unbiased estimator, the most preferred one will be that one with the smallest variance, and which means the least widely spread would be preferred. And out of these two properties, when adding the linearity as well, assumption about the parameters, so we're looking forward to have a blue estimator, which means we said what blue stands for, best linear unbiased estimator. So best means that's the efficient one, that's the one with the smallest variance. Linear, we explain what linear means. And unbiased, we explain as well what unbiased means. So that's called BLUE, or best linear and unbiased estimator. We also talk about some occasions where you will have to make some kind of trade-off between bias and efficiency. So sometimes you will have an estimator with small bias but has much smaller variance, and in those occasions we decided, or we refer that in that situation you will use the mean squared error, and I showed you the formula how to calculate the mean squared error. But what I'm going to do now, I will show you an example of two estimators. We've got information about two estimators here. Let's say theta hat and theta tilde, and then we understand that the population parameter, let's assume that we know it, which is 2, and here the variance of the first one, which is the theta hat, the expected value first is 2, and the variance is 1.5. If the other estimator, the expected value for that estimator is 1.99, but the variance is 0.5. So what we have here, we have the unbiased estimator obviously would be the theta hat, the first one, because the expected value of theta hat equal to 2, and in the same time that which equals the parameter, the population parameter. So that means the first one will be definitely unbiased. But sometimes if you look at the variance between both theta hat here and theta tilde, we'll see that you will see that the variance with the second estimator is much smaller than the variance of the first estimator. So which one we choose? As we explained earlier last week, we need to look at the mean squared error. So here I just summarize all the information we have, or these are all the information we have about these two variables. And when we estimate, when we calculate the mean squared error of both, just let me explain quickly how we do that. So this part of the formula is just the first part of the formula. It's just the bias square. So the bias is the distance between the true parameter and the expected value of the estimator. So which the expected value of theta hat minus the true parameter theta, which is 2, and this squared plus the variance. So if you do that, you'll see the mean square error for the first one is 1.5, and for the second estimator is 0.5, which obviously smaller than the first one. In that case, we would prefer the second estimator. And this is kind of the situation you might have where you have a small bias, but you have more efficient estimator, and that's the kind of trade-off we talk about. So that's what we covered basically last week. We also covered a number of the assumptions for the classical linear regression model, and we said that the ODS provides the best approximation of the sample regression function to the population regression function under certain conditions, and those conditions make the ODS estimator is blue. Just remember, that's what we're looking forward to have. We're looking forward to have best linear unbiased estimator. So what are these assumptions quickly? So the first assumption is that X is non-stochastic, so fix it in, which is the independent variable, is fixed in repeated samples. The expected value of the error equal to 0, or the mean value of the error term is 0. The assumption number 3, the variance of the error term is constant, and we called it sigma squared. And in that case, it's called homoscedastic error, or an error with a constant variance. And we said that this is a kind of assumption that we will be testing for whether it holds or not in coming lectures. And if it is not true, if the error term, the variance of the error term is not constant, that means the variance or the error term will be heteroscedastic error, which means does not have a constant variance, and this will be a problem. So we'll learn later on this term how to deal with that, how to test for that problem, and if it exists, how to deal with that problem. Also, assumption number 4, we talked about that the error term should not be correlated. They should be independent from each other. Anyway, so again, and that is another assumption that we will cover in another lecture, and we'll see how to deal with it, how to test for it, and if there's a problem of autocorrelation, how to deal with this problem. So let me now just tell you what we're supposed to cover today. What we're supposed to cover today and in the next lecture, so I'm just basically talking about that this week. So we need to see how to estimate the regression parameters, interpret the results, reporting the results. These 3 are very important for the assignment, which is due next week, and also hypothesis testing and goodness of fit. Probably we'll discuss this in the next lecture. But let me now show you through an example how to estimate beta 1 and beta 2, and then how to report your results and how to interpret those results. And at the end of this part of the lecture, I'll show you how to do this using eViews. So let's go to the example, very simple example. We believe there's a link, or there's a relationship between final mark achieved in an econometrics module, like the one we have now, and the percentage of lectures attended by students. So we collect a sample, we collect data about 20 students, and from last year, and the data we collected the data about final mark and the percentage of lecture attended. So this would be from 0 to 100%. Then here's the data we have. So we have the final mark, this, before I call it Y and X, and attendance, as I explained in the lecture, and I also refer to this lecture. Regression does not establish causality, so or based on the common sense, we would expect that attendance is the independent variable, final mark is the dependent variable, so that's why I label this Y. Final mark is Y, is the dependent variable. So your final mark, you get higher marks if you attend more lectures. So that means attendance is the independent variable, and final mark is the dependent variable. So that's why this is final mark is Y, attendance is X. So here's the data we have, and now what we're trying to do now, we're trying to estimate this model. So the model here is Y, which is the final mark, equal beta 1, that's the intercept, plus beta 2, and this is the slope parameter, xi, this should be the independent variable in our case, which is the percentage of lectures attended plus an error term. So let's assume that that error term or disturbance term, as we explained before, has all the normal properties associated with the classical linear regression model. So our task now is to find the values of beta 1 and beta 2 through OLS. So we use OLS formulas as we show in the lecture last week. So let me just remind you, so here's the formulas to obtain the OLS estimators of beta 1 and beta 2. So for beta 2, this is the sum of xi, yi, which means you will multiply each value in xi, in x, by each value in y, and then this will be another column which is xy. Minus n is the number of observation. If you remember, we obtain data or collect data about 20 students, so n equals 20, that's the number of observation. X bar and y bar in this formula are the average or the mean of x and y, so that is the sum of x divided by the number of observation, the sum of y divided by the number of observation, which is 20. Divided by the sum of xi squared, so basically you will need to get xi squared and then you sum, then minus 1 over n times the sum of xi, and you square that. So beta 1 hat, which is y bar, so you can obtain that by y bar minus beta 2 hat x bar. So these two formulas explain to you how to get the average of y and x. So here's what you need to do. So this is the data. So this is the actual data. You have the first column of the dependent variable final marked, which is y, attendance is x, and now you need these three columns here. So you need x times y. So this is xy. So you multiply this by this, x squared. So you get this. You square this each value in this column, and then y squared. Do the same thing for y. Then all what we need to do here is just this. You sum all this. So you sum the first column, sum of the second column, which is x, the sum of xy, the sum of x squared, the sum of y squared. Then when we move to the next part of this, what we need to do here now is to what I did here, just I just wrote this information again. So what we have from the previous table, so the sum of y, sum of x, sum of x, y, sum of x squared, sum of y squared. So what we need to do now is we need to just use the formula we had before, and this is the sum of xi, yi. So we already have this, which is this number. N is 20. X bar, y bar, we already calculated this. So we have those here, and then divided by the sum of xi squared. So this is this number, and then 1 over 20, 1 over n times the sum of xi squared. So once you do that, you just very easy, very straightforward. You get the value for beta 2 hat. Then you use that formula for beta 1 hat, so it's y bar minus b2 hat x bar, and this will give you a value for beta 1 hat. So now we have the two values. We use the all estimator formula to obtain the two values for beta 2 hat, beta hat. How to report these results? You need to write the equation, and now we know these values. Now we need to write the equation just to show that we understand. So why this estimation? 11.18 or point, if you want to just apply plus points. So this is set, and this is plus 0.7. This is the coefficient x. So now it comes to the second, the third step, when you should interpret the results. Remember, as I explained in the lecture, the software can do that for you, so you probably wouldn't need to go through all this calculation, but I ask you to do that by hand for at least once or twice, just to learn how it works, and then we have the results on the screen. You're able to explain this. So the most important thing in all cases is that how to interpret the results. So since we have them now, so we need to look at them more closely and see how to interpret those results. So if I were to spread the slope coefficient, there's this number here in front of ai, so that a unit increase x, for a unit increase x, so if x changed by 1 unit or increased by 1 unit, the dependent variable will increase. Again, I say increase because the sum of the slope coefficient is positive. So if x increases by 1 unit, y will increase by the slope coefficient, which is 0.73. So, but given that the units here are percentage, so x and y both are measured in percentage points. So that means for 1 percentage point increase in attendance, which is your independent variable, the average module mark, this is the dependent variable, is predicted or is expected to increase by 0.73 percentage point. Again, this is just rounded to 2 decimal places. So what about the intercept? So the intercept show you when x equals 0, how much y would be on average, and we explain why we should say an average before in the lecture last week. So the idea here is that x here is attendance. So if you attend no lectures, then on average your mark will be, so x here is 0, your mark will be 11.19%. So that's what you get achieve. That's how much you're going to get in the module if you attend no lectures, if x is 0. Great. So what about eViews? How to do this in eViews? In eViews, let's assume that you already have the data entered in eViews. And as I explained in the lecture, there are two ways to do regression in eViews. One, to write the command and eViews and enter, and then eViews will do it for you. But the easier way is to use the menus. So if you want to use the menu, so as explained in this slide now, so you go to Quick, and then from Quick you go to Estimate Equation. Once you do that, you will have the screen, and now you need to write the equation you want to estimate. And in this case, now we want y is the dependent variable, so you always start with the dependent variable, space, you put c is the intercept if you want to include intercept. And so this is a reserved symbol for eViews to understand it as the intercept. So this is beta 1 in the equation, and then x here is the independent variable. So if you look at the next box here, show you that the method we're using here is least squares, and that's by default, so don't change it because that's what we're using here. That's what we want to use, least squares, and it shows you the how many like the number of observation in your sample. So then you press OK, and here is the results. So the results here, you have the dependent variable, so eViews report which dependent variable you use, and report the method, the date when this was done, the sample, and the number of observation in your sample, and the number of observation included in this regression. So what we're going to be looking at for now, we're going to be looking at those two values of the coefficients here. So this is the intercept as we calculated using the formula. It's 11.18514, and so this is the intercept. And the slope coefficient is 0.726581. It's exactly what we have calculated using the formula. And again, the interpretation will be the same way. So for your assignment, you don't need to do that by hand. You need to use the formula. Please use eViews and report your results. And the same way I explain it now, and interpret the coefficients in the same way. Okay, so that's the first part of the lecture today. And now we move to the next part, which is the hypothesis testing. But to learn about hypothesis testing, we first need to learn about interval estimation. So in the next video, I will explain what we mean by interval estimation, how this is important for understanding hypothesis testing, and what we actually mean by hypothesis testing. So what we did so far is how to obtain the estimation, how to do the estimation, and then how to report the results, and how to interpret the results. In the next video, as I said, I will start with what is hypothesis testing, why we do hypothesis testing, and to understand hypothesis testing, we need to start with by looking at interval estimation. And in the last part of the lecture, after finishing hypothesis testing, we will look at goodness of it. So see you next video. Thank you.